Welcome to MIT Inotherm Colloquium number 11. I'm John Leonhardt of the Department of Mechanical Engineering at MIT, and I'm proud today to introduce this panel. We are going to discuss today the most important heat transfer problem on Earth, which is the energy balance on our planet. This balance involves vast amounts of energy, and it's sensitive to small changes, and the consequences of those changes can have ramifications for all life on Earth. Next slide, please. Our panelists today include a distinguished group of scientists working on climate. We have Dan Murphy from the National Oceanic and Atmospheric Administration, Veerabhadran Ramanathan from the University of California at San Diego, Kyle Armour from the University of Washington, and Graeme Stevens from the NASA Jet Propulsion Laboratory. Our moderator today will be John Marshall from MIT. Next slide, please. Professor Marshall is in the Department of Earth, Atmospheric, and Planetary Sciences at MIT. He works on oceanography and climate. His research concerns circulation in the ocean, coupling of the ocean to the atmosphere, and the role of the oceans in climate. John, the floor is yours.
Okay, sorry, I had to unmute myself. So, yeah, we're going to be talking about Earth's energy budget today. So here's the, I'm going to make some introductory remarks and then introduce our panelists. So here's the Earth bathed in radiation from the sun. And of course, the Earth warms up and then radiates energy out to space to establish an equilibrium. And so this morning, we're going to discuss the processes involved in establishing this energy balance and what we know about it and how it's changing as human activities perturb it. So the incoming solar flux is in the visible. It's reflected by white surfaces such as clouds and ice. The outgoing radiation, in contrast, is in the infrared. And it so happens that molecules such as water vapor, carbon dioxide, methane strongly absorb in the infrared. And due largely to the burning of fossil fuels, we're returning to the atmosphere in just a century or so, what took millions of years to bury in the coal and oil reservoirs. So this is a big step function change in the greenhouse concentrations in the atmosphere, and this is perturbing Earth's energy budget. And so to discuss this, we've got four very eminent scientists who are going to talk about different aspects of this problem. So I introduce Dr. Daniel Murphy. Dan is a lead scientist at NOAA's Chemical Science Laboratory in Boulder, Colorado. He's a world authority in aerosols and their roles in cloud nucleation and applications of mass spectroscopy to cloud microphysics. He mounts aircraft missions to observe clouds in the field. And he also has a kind of big picture view of how everything fits together in this global energy budget. And he's going to talk to us indeed today about Earth's energy balance to set the scene. Our next panelist is Professor Ramanathan, or Ram as he's widely known. Ram's a distinguished professor of atmospheric and climate sciences at Scripps Institute of Oceanography at UCSD. And he's made many fundamental contributions to climate science. For example, he was the first to establish that non-CO2 gases are a major contributor to warming of the planet. And much of his research is at the nexus of climate, pollution, and policy. And so today he's going to talk about anthropogenic aerosols. Our next panelist is Kyle Armour, who's a professor at the University of Washington in Seattle. And his research bridges between the atmosphere, the ocean, and the cryosphere ice processes. And he has a particular interest in polar processes. I think of Kyle as one of the big thinkers about climate sensitivity and the role of ocean in climate. And he's going to talk to us about how the ocean buffers climate change and what it's telling us about Earth's radiation balance. And our fourth panelist is Professor Graeme Stevens. And Graeme is director of the Centre for Climate Sciences at JPL. He's held faculty positions at Colorado State here in the US and at University of Reading in the UK. He has very broad interests in climate science and has made many contributions in studies of cloud feedbacks, radiative transfer, and he's a pioneer in Earth observations from space of clouds, precipitation, Earth's albedo, and indeed Earth's energy budget. And that's what he's going to talk to us about today, how we observe Earth's energy budget. So the state of play is today we're going to have a 40-minute presentation. So each of our panelists will speak for 10 minutes or so, and we're going to have a discussion and wrap up maybe for 30 minutes. And to provide input to the panelists, we would like you to use the question and answer button in Zoom, which is indicated here on the top right. And these questions are visible only to panelists, not to other attendees, and we will curate them and bring them forward. And you might also, we encourage you to submit suggestions you might have for future topics and speakers for this, series. Now, the colloquium is being recorded and will be posted on YouTube. This may include questions that we can't get to today. And if you prefer your question to be anonymous, please let us know, and your name won't be mentioned. So we're also going to kick off each panelist with each presenter will, we're going to have a quiz to set up the presentation. And so at the top of your screen, maybe it's at the bottom, on mine it's at the top, there's a poll button here. And we're going to ask you now to answer a multiple choice question, and then we'll see what you think and present the results, and this will set up the presentation to follow. So the first quiz question is, solar radiation heats the Earth, and this heating is balanced mostly by three possibilities: infrared emission from the atmosphere to outer space, infrared emission from the oceans to outer space, or 3, conduction of heat to the cold vacuum. So we'd like you to go to the button, polls button, and let us know what you think. We'll give you a minute or so to do this. We have over 50% of you already voted, 56%. we should all get out and yeah, so there's a 80% voted. So let's end the polling now. I'm going to end polling and then share results. Can everybody see these results? Yes. So, thankfully, very few of you spoke about conduction of heat in the cold vacuum to outer space. Most of you went for emission from the atmosphere and also emission from the ocean, more or less even split. The correct answer is infrared emission from the atmosphere to outer space. So this is one. So we'll hear much more about this now from Dan Murphy, who's going to talk about Earth's energy balance. So I will now hand over to Dan. I'm going to stop sharing.
Okay, went to the wrong page. Okay, is that shared properly now? So I'm going to talk about contributions to the global energy budget. And this is, as was said in the introduction, applying heat transfer to the Earth as a whole. What heat is coming into the Earth, what heat is leaving the Earth. And in this case, because the Earth is surrounded by the vacuum of space, there's no heat conduction, there's no convection, it's all radiative heat transfer. And in round numbers, the sunlight coming in, averaged over the Earth day and night, is about 340 watts per meter squared. About 100 watts of that is reflected, and thermal emission from the Earth to outer space is about 240 watts per meter squared. And we'll hear a lot more in Graeme's talk later on the details of these numbers, getting beyond what just the big round numbers I have here. I want to emphasize that small imbalances in these numbers are important. And I just did a representative calculation here. If you have 1 watt per meter squared imbalance of energy coming in and out of the Earth, it would heat the top few hundred meters of the ocean by more than 10 degrees centigrade Celsius in 100 years. And clearly the Earth, temperature was not going up and down by 10 degrees, and that's 18 degrees Fahrenheit every 100 years. So aside from a few big volcanoes, brief for a year or two, the Earth over century timescales before industrialization was balanced on order of 1/10 of a watt per meter squared over century timescales. And that's out of 340 coming in from the sun. So the Earth has to be heat transferred to have a stable temperature. The heat balance has to be to a tiny fraction of 1% of the energy going in and out for the Earth to have a stable temperature. I'm going to go here a little bit to what the greenhouse effect looks like in this heat transfer viewpoint, because we talk a lot about, carbon dioxide traps heat. Well, how does it do that? And you can see that from heat transfer. So if you say there's 240 watts per meter squared going out, and that's proportional to temperature to the 4th, sigma here is the Stefan-Boltzmann constant, and the emissivity of the Earth is high, you can solve this for the radiative temperature of the Earth, which is about 255 Kelvin. And it actually depends, it's different at different wavelengths in the infrared, but just the big average is about 255 Kelvin. Now this is about 0 degrees Fahrenheit. This is clearly a cold temperature. This is not the temperature of the surface of the Earth where we live. It's considerably warmer at the surface. So the reason the Earth is emitting at a temperature of about 255 Kelvin is that most of the thermal emission is coming from the atmosphere. And as you go up in the atmosphere, it's colder than it is at the surface. And that's why we have that emission temperature. And so how does the greenhouse effect work? Greenhouse effect gases make the atmosphere more opaque in the infrared. that means that the emission comes from higher up in the atmosphere. Higher up in the atmosphere is colder, the radiative temperature goes down, and the amount of thermal emission goes down. And then the Earth, meaning the surface and atmosphere of the Earth, warm to reestablish essentially the same 255K radiative temperature, but now at a higher altitude than it was before the greenhouse gases were added. I'm going to move here from talking about radiative fluxes, watts per meter squared, to talking about energy conservation. And you do this simply by integrating over the entire surface of the Earth, and you integrate over time. And the units go from watts per meter squared to joules. And in some sense, it's a little trivial to say we're just going to add up everything for 10 years over the surface of the Earth. But in a sense, it changes things, because instead of radiative fluxes just having to be sort of approximately balanced, there's rigorous requirement for energy conservation, and we can now apply energy conservation to the Earth. And when I show you the numbers that come up, I'm doing calculations only for the anthropogenic changes to a balanced Earth. So the numbers don't include the 340 watts per meter squared going in. They only include the 1 to 2 to 4 watts per meter squared numbers that are the changes. And the term for anthropogenic changes to a balanced Earth is called climate forcing. So when you hear the term forcing in discussions of climate change, that's what forcing means, changes to a balanced Earth. So these are the positive terms in the global energy budget, the big positive terms. So this is what's been adding energy to the Earth. And when I show you the different terms, in each case, I'm going to try to tell you where the numbers come from. And the numbers here come from measurements of gases like carbon dioxide in the atmosphere and radiative transfer calculations. We have extremely high confidence in all these numbers, and uncertainty is less than 15% in the energy numbers on this slide. And I'm starting the integration, how much heat we've added to the Earth since 1958, because a lot of the observations, especially the ocean, got better then. That was the Sputnik era. There, I show this postage stamp of the International Geophysical Year when people went out and made a lot of observations. So this is the amount of energy as a function of the year. And because of energy conservation, we have to explain what happened to this energy. It has to go somewhere. The other thing I'd like to say is that these are really big numbers. I mean, we don't normally work in units of 10 to the 21st joules. So I have, one point down here that 55 on the vertical scale, which is one of the small tick marks, is enough energy to boil all the water in all of the Great Lakes. Not just heat it to the boiling point, but actually vaporize all the water in the Great Lakes is one small tick mark. And another thing to realize is that the energy trapped by carbon dioxide, that sort of reddish block, is much larger than the heat released from all the coal and oil ever mined and pulled out of the ground that you got from burning it, that the carbon dioxide traps much more heat than was ever gotten from burning all the fossil fuels. So we're going to start in on some other terms, and another important term in the energy balance has been major volcanoes. So after major volcanoes like Mount Pinatubo, there's aerosol in the stratosphere, and that reflects some sunlight. And the blue area here, which is going downward because it reflected some sunlight, so we have less energy coming into the Earth. It's based on satellite measurements of the stratosphere, at least for the last 2 major volcanoes, and again, radiative transfer calculations. And again, we have pretty high confidence in these numbers. The uncertainty is a little larger than the greenhouse gases, but still pretty small. And so we have now this lower curve with volcanoes, and we have to explain all this energy, what has happened to all this energy. So some of the energy has gone into heating the Earth, and this is down here, I'm putting it on the bottom. This slice of energy is the amount of energy that has gone into heating the oceans. And you get this simply by measuring the temperature of the water in the oceans all over the world, and you know the specific heat of water. And there are good observations in the upper ocean, less good observations in the deep ocean, and Kyle will be talking about some of this in his talk. And other heat uptake, like how much energy it takes to heat the atmosphere. It takes a lot less energy to heat air than it does to heat water, so that's pretty small. So this is the energy that's actually gone into heating the oceans. It's an important term. And then finally, for allocating the rest, there's two other things, big terms in the energy balance. One of them in red is energy that's radiated to space. The Earth has already warmed by about 1 degree centigrade. And we have high confidence in those temperatures. And so a warmer Earth, warmer objects radiate more infrared energy. And here I've used a scaling term to the temperatures that's based on constraints from satellite observations and also based on results from climate models. And this has a pretty big plausible range. 1.4 in these units is a best estimate, but it could be anything from about 0.8 to just over 2. So that red slice could get larger or smaller. And then finally up on top, the rest of the energy has been balanced by aerosols that are largely but not entirely white, and Ram will talk about this. And they reflect sunlight to outer space, and that has balanced some of the energy. It's an extremely complicated problem, and it's so what I've done here is I've just left it white as the balance between the energy that we have to explain, the thick black curve, and the energy that we sort of know where it went, the ocean and the radiated to space. It's interesting to look at the magnitudes of some of these things, that if you look at the aerosol, the negative forcing from aerosols, the cooling due to aerosols has massed about half of the greenhouse gas forcing. And important thing is that aerosols are short-lived and greenhouse gases are long-lived. And so you can't balance these things forever because the greenhouse gases build up in the atmosphere. And if you were going to try to maintain this balance forever, you'd have to add more and more and more aerosols to the system. Only a small fraction of the energy trapped by greenhouse gases has gone into warming the Earth. And this, when I first ran these numbers, it was about 10 years ago, it surprised me then. And I think it surprises a lot of people that of the energy that's trapped by CO2, only a fifth to a tenth or so has actually gone into warming the Earth. The rest has either been radiated to space or has been balanced by the aerosols. And thermal radiation from a warming Earth is an important term already in the energy budget, even though we certainly don't have the amount of warming that we expect in the future.
Dan, 10 minutes is up. Okay.
And if we knew the aerosol and cloud, if we knew these terms because of the energy balance, we could use them to constrain each other. And one more little update. On the left, I have a figure from my 2009 paper and my update that I did recently, and they look very, very similar, except out of 60 years of energy, 40% we've put in the last 10 years, which I think is very sobering for what we're doing to the Earth's climate, that 40% of what has happened in the last 60 years has happened in the last 10 from an energy point of view. So conclusions, energy conservation, it's a powerful way. And in terms of what happens to the energy trapped by greenhouse gases, there's three big terms: energy reflected by aerosols, energy emitted to space by a warming Earth, and energy that goes into heating the oceans. So thank you all.
Thank you, Dan. Okay. So we're going to move on to our second short presentation by Ram, and we begin with a quiz question. Let's imagine that we stopped emitting aerosols into the atmosphere and we kept greenhouse gases concentrations the same. Now, would the Earth's surface, would it warm would it cool, or would it stay the same temperature? And I have to say, the panelists, we all had a great discussion about this question. Good, we're up to about 70% voted. Okay, so let's end polling now. We've got a good response. So here we go. So 74% of you said that you felt that the Earth would warm. Remember that we kept greenhouse gases constant and just cut the aerosols. Some people thought that it would cool, a few stay the same temperature, but overwhelmingly the consensus was that it was going to warm. The correct answer is we think it will warm, although as Ram, I'm sure, will tell us, this is a rather complicated question. It depends on time scale, lots of things. Well done, everybody. So stop sharing results. So now we're going to have Ram talking about anthropogenic aerosols. So over to you, Ram. I'm going to stop sharing.
Thank you, John. John, can you see my PowerPoint mode?
Yes, we can see that, yeah.
Okay. Oh, it's on the last slide. So, John, I'm not able to get the...
So it's at the bottom right, Ram. There's a little, there we are. Click on that, yeah.
Yeah, great. Okay, Dan gave us an excellent summary of how we as human beings are altering the energy budget of the planet in a major way. He mentioned about aerosols, so let me pick it up from there. What you're seeing is a picture I took from the cockpit of a DC-8 aircraft in the Arabian Sea. We are flying it around 5,000 feet from the sea surface, about a mile, and about 200 miles downwind of Mumbai or Bombay. So why is the sky brownish? Basically particles in the air, they are either scattering light or absorbing light. In this case, we see more of the absorption by soot. I think many of us know this as Denver brown cloud, except what I'm going to talk to you is that these brown clouds or aerosols are everywhere in the planet. Typically, these particles are about 1/10 of a micron, which is a millionth of a meter. A micron is a millionth of a meter. So these particles are about 1/10 of a micron size to about 2 to 3 microns. So what's the source of the emission? Of course, automobile exhaust. The black stuff you see coming out of the car tailpipe is either soot and also gases such as NOx. All of them become particulates. And I show here this shape of this particulates. The other major source in developing nations is cooking with biomass. There are over 3 billion people who are still too poor to afford fossil fuels. So how do they become from a local source, from an individual cook stove or a tailpipe? Here you see a satellite image of a river of pollution coming from the Indo-Gangetic plains. And I want to show you that, lest you think this is an India problem. So this shows aerosols captured from satellite. You know, we call them aerosol optical depth, but you don't have to worry about the technical details. Just think of the, how many particles are there. It's basically a measure of the number of particles in the entire column. So you see from the east coast of the US, all the coal-fired power plants and the automobiles. And I've documented how fast it travels. For example, China, air pollution from China travels to the US West Coast in about 4 to 5 days. And likewise, pollution from the east coast of the US travels to Europe in about 2 to 3 days. So it is a global problem. So now let's look at why we should worry about this. So this is a cartoon of the various ways aerosols impact, just starting from the left. And the yellow arrow is the incoming sunlight. Basically, these particles scatter light. And this has been documented from space. You see it from satellites. It's making the planet brighter. On the other hand, these aerosols also absorb sunlight, mainly green and blue. That's why the brownish color, soot, is the major absorber. And then the aerosols scatter sunlight back to the surface, and that's why the sky is hazy. Okay, so that's on the left-hand side. Mainly the effect is cooling. And then, as you know, sunlight is reflected back by the surface and clouds, and that reflected radiation would have escaped to space. Dan showed that to be about 30% of the sunlight is reflected back to space. But these aerosols intercept that light and they, like soot, absorbs them. So that reduction of the reflected light by absorption causes heating. The aerosols also influence the cloud properties. Most of the water vapor drops are formed on aerosols. So they include the number of clouds, which increases the reflectivity from the clouds, a cooling effect. And they also suppress rain formation because they're not allowing the larger raindrop size to develop. Okay, so they intercept a number of ways. The major thing I'm going to focus on is what's called dimming. You can Google global dimming. There will be about hundreds of papers which will show up, all written between 1990s to 2000. So the dimming happens because of reflection. And the second, very, very few recognize this, the absorption of light is a major source of dimming at the surface, all right? So how do we get your hands on this complex problem? So we did a major field study. This was myself, Paul Crutzen, famous chemist from Max Planck, and Dr. Mitra from India. Basically, in the wintertime, you have air flowing from entire South Asia into the Arabian Sea. So we took about 6 aircraft, 2 ships, and we even moved a satellite from the European satellite over the Indian Ocean. So we would go north and south, starting from Maldives, where we were in the thick of the plume. We will cross to the southern hemisphere till the pollution was near zero. So we had over 40, 50 instruments, and for the first time able to quantify what exactly was this aerosol doing. I'll show you one of the most dramatic pictures. This was taken by a former postdoc of mine. See, he's sitting on the ship, all right, going in and out of the pollution. Just follow the yellow curve called direct. So he's directly looking at the sun, it's a spectrometer. So the peak is in the visible wavelengths, 0.4 to 0.7 microns. You see that the pollution cuts down the direct sunlight by almost 30%. That is the source of the huge dimming. But the aerosols also scatter light, so the diffuse light goes up. So that's why when you're in this pollution cloud, you can't see the sunlight. The sunlight becomes hazy. So for the first time, it was captured exactly how this particulates, what wavelengths, etc. All right. So now let's all put it together. Yeah. So what we did was we need to help models. We came at it independently. We set up a lot of surface observatories. We flew unmanned aircraft long before Amazon discovered unmanned aircraft. We had a number of instruments on them and satellites. So I want to show you the picture we put together globally. So this is global average perturbation of the energy budget of the planet as of 2015. The gases were all done by IPCC, and this is the Intergovernmental Panel on Climate Change. Over 1,000 scientists were involved in this. So in terms of watts per meter squared, the surface area is equal to the heating of the planet, okay? So carbon dioxide traps about 2 watts per meter squared. Think of these greenhouse gases as a blanket. Just like a blanket traps your body heat on a cold night, these gases act like blanket. And then there are a number of other gases. Again, Dan Murphy mentioned that. And we call them super pollutants simply because per ton, these other gases are anywhere between 20 to 20,000 times more potent than CO2 per molecule, per ton. And then comes black carbon. You see this little circle. So that is the energy trapped or sunlight trapped in the atmosphere by soot. Okay, it's part of aerosol. So on the right-hand side is all the cooling aerosols, sulfates coming from coal combustion, nitrates from automobiles, organics by burning of firewood, and others. They are mostly scattering. So they're cooling aerosol, and I think of them as masking. So if you see the number, the aerosols are masked as much as half of the total warming. Okay, I think it's very close to what Dan showed. So let's go on the regional scale. The main issue, this problem has been somewhat intractable, is that it's not globally uniform. On the top is where we see the emissions. You see from the ships, from the aircraft, the entire Atlantic emission is from the aircraft. And then you see the local hotspots. The one below is the heating by soot, okay? If you see the magnitude, it's in the order of 10 to 16 watts per meter squared. Much, 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 much larger than the direct forcing of greenhouse gases, but they are concentrated locally. Then you see the dimming at the surface as much as 15 to 20 watts. So while
you've had 10 minutes.
Okay, I'll just wrap it up then. I'll go to the last one.
Well, you can speak for 1 or 2 more minutes, but
okay. So the main thing is, how do we know what's all happening? The primary thing about the dimming is that 80% of this radiative heating of the surface is balanced by evaporation. So the proof of the dimming is when aerosols go up, the planet dries out. And this was documented because the aerosol emission went up from 50s to 90s, reached a peak, and then came down. And this was documented by a Swiss scientist. You see the global rainfall came down and went back again. So I finish up with the last one. This is, in fact, one of the most important issues we are struggling with in understanding how human beings are altering the heat budget. So I show the greenhouse forcing, and then I show the aerosol mask, okay? We have to clean up the air because these particulates are killing about 8.5 million people every year, just pollution. And then it's cutting down the rainfall. So the question is, when you cut down the aerosol emissions, what's going to happen to the planet? Is that going to heat up? Because it's unmasking, or will we bring down other emissions? We finally have a spectacular experiment we are all performing because of COVID. During March to May, this aerosol emissions have come down globally, particularly in places like India and US and Europe. we have documented almost 50% reduction. So we now have scientists have a fantastic opportunity to make detailed measurements and understand what the aerosols are doing to the planet. Of course, I'm not suggesting COVID is an exciting development. It's a disaster, but there is some scientific payoff. Thank you, John.
Thank you very much, Ram. So let me share my, okay, so Ram has spoken a bit about the role of anthropogenic aerosols, and now we're going to talk about the role of the ocean in global warming. So let's start off with a quiz question again. So the question is, rising concentrations of greenhouse gases cause more heat to be retained by the Earth. What is the primary way that that energy is stored? Does it stay within the atmosphere? Does it warm the land? Does it melt ice? Or does it warm the oceans? And I think some of this material is kind of being covered as we go along. So we've got 76%. Let's have a few more votes. Right, let's end polling and share the results. Everybody see the results there? Well, well done, everybody. Most of the heat goes into the oceans. That is the correct answer. The heat capacity of the atmosphere is very, very small, so it can't really store much of the heat, but some of the heat does melt ice, and a small amount goes into the land as well. Okay, so we're now going to move on to discuss the role of the ocean in all this, and I hand over to Kyle Armour.
Great, thanks, John. Can you hear me okay?
Yes.
Great. All right, so I'm going to talk about ocean warming today and the role of ocean warming in global warming. I want to just start off with a figure showing the rise in global surface temperature since the 1800s. A bunch of different groups around the world using the same basic data of surface temperature observations over the oceans and land produce a rise in global temperature of about 1.2 degrees since the 1800s. And that 1.2 degrees will become important in just a minute. But that's the global surface temperature change we've seen over the last 150 years or so. Now, what's causing that is an energy imbalance in the climate system. Dan already talked about this a little bit. We have these large fluxes coming in, incoming solar radiation. Some of that is reflected, about a third or a little bit less than a third of that is reflected back to space. We have outgoing long wave radiation, but we think that the imbalance between the incoming radiation and the outgoing radiation right now is about 0.8 watts per meter squared, a pretty small residual between very, very large energy fluxes in and out of the climate system. But that imbalance of about 0.8 watts per meter squared is what's driving the global warming. And we think that most of that has been due to basically increasing greenhouse gases in the atmosphere, canceled somewhat by aerosols. Another thing I'll point out on this diagram is lots of numbers here. At the top of the atmosphere, this is all radiation. At the surface, you have solar radiation partly being balanced by radiation out toward the atmosphere in long wave, radiated like sigma t to the fourth. But then you also have these other terms which are sensible and latent heating, latent being evaporation primarily off the ocean surface, meaning that the surface energy budget is much, much more complicated than the top of atmosphere because you have other terms involved, in particular evaporation. The other thing I'll point out is these large uncertainties in the surface energy imbalance and the top of atmosphere energy imbalance. So what I want to talk about today is how do we end up with fairly small uncertainties in the amount of energy being stored in the climate system when we have these large uncertainties in the other terms. So the first thing I want to do is just give a quick sense of why it's about 0.8 or about 1 watt per meter squared imbalance. And so to do that, we can just think about the radiative forcing that Dan introduced coming from different terms, different atmospheric constituents changing. So CO2 has added about 2.2 watts per meter squared of extra energy to the climate system today. Methane, aerosols has actually blocked some sunlight, but altogether that adds up to about 2.5 watts per meter squared with pretty large uncertainty. We've seen a global warming of about 1.2 degrees since the 1800s, which has been damped at a rate of about 1.4 watts per meter squared per degree Kelvin or per degree centigrade. If you combine these things, you can think about a simple energy budget equation that says the energy imbalance is the forcing minus lambda T, where lambda is that radiative response multiplied by the observed warming we've seen. So just putting all these together, about 2.5 minus 1.2 times 1.4, that ends up with about 1 watt per meter squared energy imbalance. Now, unfortunately, this isn't accurate enough to really know the energy imbalance because we have large uncertainties in the aerosol forcing and we also have large uncertainties in this lambda. But it gives you an overall sense that the energy imbalance should be around 1 watt per meter squared. How we actually get that number is observing where that energy is going in the climate system. So we think it's about 0.8 watts per meter squared right now. And the basic way we get this is by observing the oceans. And the reason the oceans are so important is because they are the largest heat reservoir in the climate system. So just to give you a sense of that, the entire atmospheric column above a point in the ocean has the equivalent heat capacity to about 2 meters of seawater. And because the oceans have an average depth of about 4,000 meters, they're going to dominate the heat uptake and heat storage in the climate system. So we think something like 93% of the energy coming into the climate system, the excess energy coming in are being stored in the oceans. And the figure on the right is showing observations of these different components: upper ocean, deep ocean, ice, land, atmosphere. And this is telling you energy storage over time. And you can see the atmosphere, the land, the ice are fairly small components compared to large storage of energy in the oceans. So how we basically get the energy imbalance is by observing the oceans and measuring the energy storage there and trying to also estimate how much is going into the land and atmosphere. Earlier, Dan gave us a sense of how much energy this is. About 55 zettajoules or 10 to the 21 joules is enough to boil the Great Lakes. We've actually observed in the global oceans about 150 zettajoules of excess energy absorbed since 2006. Now, if you just take that 150, divide by 13 years and divide by the area of Earth, you get about 0.7 watts per meter squared global average energy storage in the oceans. If you combine that with what we think is about a 0.1 watt per meter squared energy storage in the atmosphere, land, and cryosphere, that is melting ice, you end up with about a 0.8 watt per meter squared, plus or minus a pretty small uncertainty. And you can see that here, it's basically the slope of this line divided by the area of Earth. We'll get you that 0.8 watts per meter squared. So that's how we know it accurately. It's basically observing the oceans. I'll talk about those observations in just a second, but I want to also talk about what this has meant for global warming. So I said earlier that we've observed about 1.2 degrees of temperature rise in the last 150 years. The oceans have saved us from about 0.6 degrees of surface warming since the 1800s. And you can see this in a couple ways. The first is just that the ocean has taken up and stored about 0.8 watts per meter squared, as I mentioned. This is about 33% of the total forcing we think is around 2.5 watts per meter squared, mainly from CO2. So that means that we have, already warmed 1.2 degrees, but that's only 66% of the warming we would have seen if the oceans hadn't taken up the heat. And so the oceans have saved us from about 0.6 watts per meter, or 0.6 degrees, I should say. Another way you can see that is just by rearranging this energy budget equation. Earlier I said this is the energy imbalance N, the forcing R, lambda T is the radiative response. If you just divide through by lambda, this term you can interpret as the warming still to come. This term is the equilibrium warming if we held the forcing constant at today's levels. We fix greenhouse gas concentrations and aerosols, and that's about 1.8 degrees Celsius. And this is the warming we've seen so far. And so this term, again, is about 0.6 degrees. That's how much committed warming we would have if we were able to hold the atmosphere fixed at present day conditions and let the oceans continue to warm up to match the atmospheric temperatures, essentially. So the oceans have been a big hero in global warming and saving us from about a third of the warming we would have seen. Now, how do we observe the oceans? Why do we know this? How we used to do it from, say, the 50s to the 90s is basically research ships running along the ocean, taking measurements as they go, creating these long hydrographic sections of temperature and salinity. But you can see those observations all put together are fairly sparse. There are whole swaths of the oceans where we just don't really have observations from that period. And so you're trying to reconstruct what the global oceans look like from a pretty sparse record. How we do it now, since about 2002, is we use primarily autonomous profiling floats. So this is an example of those floats called Argo floats. How they work is they basically have a bladder, a hydraulic pump that basically inflates or deflates as they go up and down the water column. They drive the float to move up and down the water column by changing its buoyancy by inflating or deflating that bladder with a hydraulic pump. And they're about the size of a person, you can see here, lowering into the oceans. And they basically live for about 2 years in the oceans. They drift around with the currents and they measure the water column. And they basically work by relaying to satellites information. They then sink to a depth of about 1,000 meters. They drift for about a week, and then they profile over a depth of, they drop down to about 2,000 meters, and then they come back to the surface. And that whole thing takes about 10 days. Now, what I want to show is basically the coverage of these things. So I'm going to show a video of where these are in the ocean as a function of time. And so starting in about 2001, we started to put these things in the ocean. You can see up here the total number of them. And every red dot is an Argo float, and you can see the little tails behind them. That's telling you where they've been in the last 100 days. So I'll just let this run for a minute. And so 2002, quite a few floats are up to about 500. You can look at them drift around. What you're seeing here is the drift of the floats at about 1,000 meters in the ocean. So they tell you a lot about the temperature and salinity. The new ones also tell you about things like oxygen or CO2 in the oceans. You can start to see around the mid-2000s, we're up to several thousand of these floats in the ocean, continuously profiling the water column, giving us a lot of very good spatial coverage down to about 2,000 meters. We still aren't observing the deep ocean very well, but this is kind of ongoing efforts to start to observe that by putting in deep Argo floats that can go down to 6,000 meters. As you get into the late 2000s, we're up to something like 3,500 floats. We're also starting to see floats populating the Arctic and the Antarctic. These things don't play very well with ice because they come up and smash into sea ice, but the new floats that they're putting in the Antarctic actually sense the temperature of the water as they approach sea ice and turn around and go back down and stay at depth and continuously do that over the winter until they can come back up and relay that information to satellites.
Kyle,
so
10
yes.
minutes.
Okay, great. I'll finish up in a couple slides here. So what I want to point out is this is the observed warming we see of the last 40 years. There's a characteristic shape to it, which is a lot of warming in the tropics and the northern hemisphere, much less warming in the southern hemisphere. And that's basically driven by ocean circulation. We have an overturning circulation like this. This is sinking in the North Atlantic here and upwelling in the Southern Ocean. And I point this out because this background ocean circulation very much shapes where the heat is taken up and where it's stored in the oceans. It wants to kind of shunt heat to the northern hemisphere and the Arctic and away from the Antarctic. And so the ocean circulation plays a large role in setting this pattern of heat storage. I'll skip this and just go straight to the final point, which is the warming of the oceans has a big impact on sea level. So just this final concept is per degree of warming, you expect about a 0.02% increase in volume of the ocean. And so just to give you a quick sense of how much sea level rise that is, if the upper oceans have been warming at a rate of about 0.05 degrees per year over 1,000 meters, that's about 1 millimeter per year of sea level rise. To do this more carefully, I've taken those ocean observations from Argo floats and calculated how much sea level rise we expect from ocean warming, basically thinking about the volume expansion at every level in the ocean at every location in the ocean. And this is the pattern you get. About 1 millimeter of sea level rise per year since 1993, but some places much, much larger. The final point is you can compare this to satellite observations, which are basically measuring the height of the sea surface by bouncing signals off of the sea surface back to space and measuring the time it takes. And what you see is a pattern that generally reflects the ocean warming, but the global average is about 3 times larger. And so this tells me 2 things. The first is that the ocean warming primarily explains the pattern of sea level rise we've seen. And these hotspots are basically where you've stored the heat in the ocean, which is again set by ocean circulation. And the second thing is about 2 millimeters per year extra volume of sea level has come from freshwater input, coming from mountain glaciers, ice sheets, and aquifers. But the comparison between these 2 things gives you a lot more confidence in this pattern of heat uptake because it looks like an independent observation coming from satellites. So I'll stop there. Thanks a lot.
Thanks a lot, Kyle. So we can please get your questions in so that we can return to these topics in our panel discussion. So let's move on now to the last topic. We're going to give you a quiz question first. So which of these measurements do not compromise our ability to constrain Earth's energy budget directly from observations? In other words, which of these measurement techniques or processes is the most accurate? Greenhouse gas concentrations and spectroscopy, ocean heat uptake, or top of the atmosphere radiative fluxes? So which of these measurements don't compromise our ability to constrain Earth's energy budget? So we've got 50%. Keep voting there. And to wait a little bit longer. Good, we've got up to 70% voting and things are stabilizing. So let's end polling. And here are our results. So kind of very, very interesting response. So it's a kind of split evenly between the 3. Some of you feel that the greenhouse gas concentrations are well enough known, others heat uptake, others top of the atmosphere radiative fluxes. And the answer to the question is greenhouse gas concentrations and spectroscopy. So relative to the other 2 processes, ocean heat uptake and top of the atmosphere radiative fluxes, we feel that our measurements of greenhouse gases and the background spectroscopy is rather well known. So thank you very much for that, responding to those questions. So this sets up Graeme Stevens, who's going to talk about measurements of Earth's energy budget. And Thanks. So I hand it over to you, Graeme.
Thanks, John. Continue, yeah, right. Okay, so I assume you can see my screen and everything's okay.
Yeah, we can.
Thank you, John. So since time is short, I thought I'd just jump to the really main takeaway point of the message I want to convey. And it's that we have multiple approaches to measuring the Earth radiation budget, and the success in terms of how well we do this measurement really depends on its kind of application, the sort of basic science question being posed. So I thought I would just illustrate this point around 3 questions that one might consider important from the point of view of Earth's energy balance. First would be how is the heat content of Earth changing in time, and how is this change being distributed within the Earth system? So what would be our measurement approach towards answering that? The second is the role of the different components of the Earth system play in defining these changes, such as, for example, the changes that we observe is primarily coming from atmosphere and processes that change the atmosphere versus the surface changes and so on. And then the third would be digging deeper down is what can we say about the mechanisms that produce these changes? So these are sort of three broad questions you might pose in terms of measurement strategies. Now, Kyle showed this figure, and it's basically a representation of the Earth's energy budget. All the quantities there are in watts per meter squared, as it states. And there's sort of there are layers to this figure. If you look at the top of the atmosphere, the top of the atmospheric quantities, we basically measure these fluxes in and out of Earth at the top of the atmosphere using radiometric methods, radiometers flying on satellites. The uncertainty on these measurements alone, however, are the order of a few watts per meter squared, as you can see there, as quoted in this figure. And yet the total energy imbalance, we think, as Kyle described, is less than a watt. So purely and simply just from a radiometric point of view, we can't get a handle on the imbalance just by measuring the radiative fluxes in the top of the atmosphere. So in order to answer this first question, we need something a little more involved than simply radiometric measurements on satellites. Now, as you start to peel the onion away and go deeper into the Earth and try to understand the energy flows in and out and through the Earth system to the surface, the uncertainties grow, and the types of observations or measurement strategies we invoke become much more complicated and much larger in scope. So a few of the key points to note of this from this figure to take away is the magnitude of the fluxes and their uncertainties associated with them, and the degree to which the planet's out of balance in relation to these uncertainties. And the second is at the surface, our methods to derive information about surface energy, for example, involve many, many more types of measurements other than that which we derive from the satellite at the top of the atmosphere. And we have to rely on kind of advanced assimilation kind of techniques and tools to get to these idea of these fluxes at the surface. So it becomes more complicated as you start to peel away the onion and go deeper into the Earth system. Okay, so what I thought I'd do is just give you a sort of sense of the imbalance, because what we basically developed is an independent way of estimating the imbalance, as Kyle described, by looking towards the oceans, and then using this to constrain the top of the atmospheric fluxes and come up with a kind of a constrained measurement of the top of the atmospheric fluxes to look at this imbalance and its change over time. Okay. So this is a kind of an illustration of one approach towards getting this balance, and it sort of covers the number of different aspects. And one approach that we're currently invoking is to look at the use of the sea level budget itself, and we have measurements of the different elements of this budget. We measure the total rise of sea level from altimetry. We measure the mass change occurring in the oceans from the gravity measurements of Grace. And of course, Argo provides us with the in situ measurements of the thermal structure of the ocean, which gives us a kind of an independent measure of the steric component. Now, Argo, as Kyle mentioned, samples down to 2 kilometers. And so we're missing kind of the deep ocean, and we're indeed missing other parts of the ocean. So it's kind of an incomplete sample. And trying to estimate the overall uncertainty on this under-sampled oceans is still part of a challenge in terms of the research community. However, if we've got these two measurements of the total and the mass, and the difference should be the steric, and hence we can compare that difference to the actual in situ measurement, so we get a handle on how well we can close the sea level budget, and hence how well we might have a measure of this heat uptake by the oceans, which is about, like Cole said, 90% of the total. Now, this is a figure that shows time series from the Grace time period of sea level rise in black. You take the left-hand panel. Sea level rise is in black, expressed in millimeters per year. Expressed in millimeters rather. And the green is the amount the sea level would rise based on the mass increase that Grace has measured. The orange is the difference between these two, which is the measure of the steric component. And the blue curve is the Argo data superimposed. So if everything was all closed and our understanding was tight, the blue and the orange curves would lie one on top of the other, which they sort of more or less do, except for over the last couple of years where they've departed, and we're scratching our heads trying to understand why the difference estimate is larger than, in fact, the in situ measurement itself. So this is the sea level budget, and you can interpret that in terms of obviously the heat content change. The orange is the heat content change that you would get from the difference of these two measurements, and the blue is from the Argo, and they're very, very similar. And the trend in this gives you the measure in watts per meter squared, and that's where you get something like a 0.8 watt per meter squared heat uptake by the oceans from this measurement. There are differences at the end of the period, but they are within the uncertainties which are shown in this shaded region. So we're still struggling to kind of figure out what this total heat uptake, what the overall heat energy imbalance is as a whole. The 0.8 watts per meter squared column is a number that's sort of verified by two basic different measurement types. So it gives us confidence, but there are some differences we're still trying to scratch our head over. So that's one approach to get the constrain the measurement of the top of the atmospheric radiation measurements that we're making from radiometers. And when we combine this heat uptake or this constraint to the radiometric measurements, we're able to look at the change over time of the energy imbalance of the planet. And this is the series record, which is the radiometer record, since the 2000 period. It's a 20-year record of energy imbalance of the planet derived from series where it's been constrained by this energy imbalance from this ocean data. And we actually see that the energy imbalance of the planet itself has actually been increasing over time at about 0.4 watts per meter squared per decade. And there's interannual variability associated with this. And then we're able to, obviously, because we have the radiation measurements, we can look at the different components that comprise this. We can look at the effect on the long wave changes, the emission to space, and that emission to space has basically decreased over the period of time. And similarly, we can look at the change in the reflected sunlight and the absorbed solar radiation amount, rather. So the absorbed solar radiation has increased over time and basically drives this energy imbalance change over time according to this analysis. And this increase in the absorbed solar radiation has come about because the albedo of the planet has slightly decreased over time, associated with changes in properties of the atmosphere, both aerosol, clouds, and water vapor changing over this 20-year period. But the basic question here is, the overall uncertainty, radiometric uncertainty, is larger than these changes we're seeing. And the question is, do these measurements of the top of the atmospheric fluxes have more precision, greater precision than we might assign to its overall accuracy? And how do we verify that these trends and this variability is real? This is part of the challenge we have in terms of understanding these data records, where we're seeing small change.
Graeme, 10 minutes up.
Okay, so I'll just sort of come to my last two more view graphs. Yeah, I'll skip over this one. So the third question is, what are the mechanisms that produce the changes observed? So it's quite interesting. Basically, measuring the radiation budget of the planet, but doing it spectrally, starts to provide us with fingerprints of the climate processes that shape the change. And there's two examples here I'll quickly just go over. One is the upper panel shows that The albedo of the Earth, or the amount of energy reflected from Earth, about 99 watts per meter squared, is entirely symmetric about the equator. It's exactly the same in the Northern Hemisphere and the Southern Hemisphere. Yet if we look at the spectral nature of the reflected solar radiation from measurements made from a totally different measurement strategy, we can actually see that there are differences between each spectrum. The Southern Hemisphere has more clouds and reflects more visible light than the Northern Hemisphere. The Northern Hemisphere has greater landmass, reflects more near infrared radiation, longwood of 700 nanometers, than does the Southern Hemisphere. So there's this curious balance that has spectral fingerprints of differences. Secondly, the outgoing long-wave radiation and spectral characteristics of outgoing long-wave radiation has fingerprints about the changes that are occurring and how it's occurring, and what processes are responsible for this occurring. And this is a figure that's taken from an early study with Goody. Shows you spectral radiance change in a climate change experiment as function of the frequency of the radiation. And you can see the fingerprints of CO2 change, tropospheric temperature change, moisture changes, and so on. Interestingly enough, in the far infrared radiation, shortward of 500 in these wave number units, this region shortward of 500, about 50% of the outgoing long-wave radiation in space is in this far infrared region. And it's a region we actually don't measure the radiation in. We measure the total amount of radiation leaving the planet, but we actually don't have spectral measurements in the far infrared that tell us about the processes of outgoing long-wave radiation.
Graeme, we've got about 15 minutes left for panel discussions. So if you could...
So I'll leave it here. So I'll just leave it here. We are moving in the coming time to make measurements of this spectral outgoing radiation and giving us further insights on how the radiation how the radiation is influenced by the processes that shape it. So we have these two measurement strategies to measure the outgoing long-wave radiation spectrally and the reflected sunlight spectrally, and that's coming in the next decade. I was going to give you a summary at the end, but I think we'll just leave it there and leave it for questions.
Thank you very much, Graeme. So now we're going to move into our question and answer session. And let's see, we've been curating some of the questions, and I will ask a few of them. So we have one question coming in, which is about water vapor. So water vapor is the most important greenhouse gas, but it's not explicitly mentioned in the presentation. So would anybody like to make a short comment about how we deal with water vapor and what its importance is? Maybe Ram.
Thanks, John. Can you hear me?
Yes.
Yeah. As the questioner said, the water vapor is the most dominant greenhouse gas in the atmosphere. The reason our talks didn't address that is it's a naturally occurring gas in the air from evaporation from the oceans and surface. And it's not being modified substantially by human activities. But water vapor, because of its thermodynamics, the ability of the atmosphere to hold moisture increases by about 6 to 8% per each degree of warming. And also water vapor evaporation from the ocean increases. Because of that, water vapor is the major amplifier of global warming, the so-called positive feedback. So our best estimate in almost all the climate models, water vapor amplifies the warming by about 70 to 80%. So in other words, global warming would be a lot smaller instead of the current 1 degree warming. It probably would have been 0.5 degree to 0.6 of a degree without the water vapor feedback.
Okay, thank you very much. We have another question, maybe Kyle could take this. Why is sea level concentrated regionally? You know, if you add water to the ocean, doesn't it spread everywhere uniformly?
Yeah, sure. So that figure I showed that showed the sea level rise showed that some regions are basically rising something like 3 times faster than the global average. I think the regionality of the sea level rise is primarily ocean heat storage. So there was a hot spot in the kind of Western Pacific Indian Ocean, and there were hot spots in the Southern Ocean. Those are coming from the fact that the upper ocean in those regions have warmed much, much faster than the rest of the oceans. And on top of that, the meltwater coming from glaciers, depletion of aquifers, and ice sheets, that water I think does get spread fairly uniformly over the ocean surface. So I think it's the regionality of the ocean heat storage that causes that, and that's primarily due to interactions between ocean circulation and atmospheric circulation that kind of intensifies certain regions of the storage of heat.
Okay, thank you. I have one general question for the panelists, and please chip in, and that is, if there was one thing we could do as a community to improve the, to constrain the energy budget that we've been talking about this morning more accurately, what would that be? Would it be a process study and modeling, or a new instrument? Would it be going into the ocean to, what could we do to move the dial a bit here?
Yeah, okay, so I could have a first shot at this, and of course it'll illustrate my bias, of course. We do have technology capability now whereby we think we can measure the global energy imbalance. If you want to articulate in terms of the global energy imbalance, we think that we can do this not through radiometry like we have been trying for the last many decades, but we think that we can do this now by the exquisite measurements of acceleration that have been promoted through programs like GRACE and so on, where we can actually measure exquisitely accelerations on spacecraft, and we can actually measure the photon, the radiation pressure on, and impact the radiation pressure on spacecraft far more accurately than we can measure the radiometric or the energy carried by photons. And we think that we can get down to around about the 0.1, 0.2 watt per meter squared level through photon momentum measurements. And it comes about because of the almost factors of almost 3 to 4 orders of improvement in acceleration measurements in spacecraft that have occurred over the last maybe 3 decades. And that's the sort of level of acceleration that we would need to get to that 0.1, 0.2.
But does that give you long wave and short wave?
The total. It's a total energy. It's a total energy. It doesn't break it down by components. But if you ask the question, just how much energy is coming in and out of Earth to the 0.1, 0.2, I think we can probably get there with this approach. But that's just one part of your answer to your question, I think.
Anybody else want to chip in?
I'll chip in with a couple of things. On the aerosol and cloud side, I think we can continue to chip away with more studies of the individual processes so that you don't necessarily get your global number better, but you keep chipping away at what's happening in one part of the world and what thing, and you can get it's a very slow process, but you can get cumulative understanding. The other thing I think that could be done from space is having actually more radiometers in space. And the way that helps is, like right now we have some of these radiometers going overhead once or twice a day. And if you have more of them, and for instance, they're in different orbits, or they go over at different types of the day, again, you can chip away with looking at different processes. How does the infrared emission vary between morning and evening, and how does reflected sunlight vary with time of day and things like that? And it's not going to be a grand answer, we're going to measure it to 1/10 of a watt per meter squared, but it's going to start to constrain some of the processes.
To add to Dan's, just if I just quickly can say something, I just mentioned spectral at the end. This is something that's coming, and the spectral measurements allow you to sort of tie the radiative processes, the fluxes and energy, to the processes more directly. And that's part of the way of Dan's chipping away at the problem. And that's coming in the next coming decade, but it's coming in kind of piecemeal ways, not coordinated and focused way, but it's coming in a piecemeal way.
John, can I quickly add one thing on that? I wanted to add that if our goal is just to understand global energy imbalance, the single number, I think Argo is the way to do it, in my opinion. Better and longer records of deep Argo measuring the full ocean. But I think that isn't quite enough because ocean heat uptake and storage isn't the major uncertainty right now. It's really aerosol forcing and radiation. And so that's what the satellites get you in addition. So I think I just wanted to make that distinction. I think both are very important programs for that reason.
Yeah.
So the point is, as you're getting to the next question, the point is you need all of these kinds of measurements to make advances. There's not a single golden nugget measurement that's going to sort of solve the problem. It's a kind of a collection of approaches and measurements.
What do people think about this Faustian bargain that, you know, that if we did really strenuously sort out air pollution and put less aerosols into the atmosphere, there would be negative effects in terms of global warming? I mean, is that a true statement, or is there some conflict here?
John, can I take that question?
Sure, yeah.
Yeah. I don't see it as the Faustian bargain at all, because if you think on timescales of 20, 30, 50 years, we are going to get rid of the air pollution. Okay, so there are two ways to do that: put stuff on your tailpipe to cut the emission, or completely switch to renewables. You know, solar and wind don't emit air pollution if you generate all of the renewable fuels. So, but it is clear that if we reduce air pollution without cutting the greenhouse gases, right, switching from fossil to renewables, that would be a disaster. All you'll get is warming, unmasking. So what we are advocating is that cut air pollution by switching to renewables. Then you bring down CO2 emissions, or then you bring down methane emissions. The unmasking is not a huge issue because you're also cooling the climate by cutting down greenhouse gases.
Thank you very much, Ram, for that, those comments. So it's now almost 11:30. I'd like to thank the panelists, Dan, Ram, Kyle, Graeme. It's been really enjoyable having you zooming in here, and I think it was a highly successful session. I'd also like to thank John Leonard for setting this up, and I'm going to give him the last word by sharing a screen, and he's going to tell us about the next the next symposium that's going to be set up.
Thank you, John. And thank you to all the panelists. And I'd also like to acknowledge Susan Solomon, with whom I work closely in organizing this event. She was very deeply involved. Our next webinar will be on Tuesday. We are switching from Wednesdays to Tuesdays going forward. And this webinar will be about personal thermal comfort, technologies for locally regulating your thermal environment to be more comfortable in a setting that might otherwise not be comfortable. So please do tune in for that one. Next slide. And then to wrap up, while you're all still here, please do type in your suggestions for future topics and events, speakers, format, anything else. Sign up on the email list at Inotherm to be notified of future events. And by the way, all of our past discussions and panels, and this one, will be on the YouTube site associated with Inotherm, as will the Q&A. And so questions that were posed will be archived as well. So if you missed part of this, if you tuned in late, if you had to leave early, you can catch the rest of the event on YouTube.